Yes.
Is it visible now?
Yes. Okay, it is visible now. Fine.
Okay. Thank you, sir. Now, today, the title of the webinar is Resonance-Free Mechanical Structures. Now, the structure of the presentation you can see in the slide. We are here at this particular point, and the presentation, the take home of the webinar will be how to develop resonance-free mechanical structures. For that, we will discuss the smart materials, that is something related to the piezoelectric material, electro-rheological fluids, MR rheological fluids. Then the options, how to eliminate resonance. Then the resonance, whether it is advantage or disadvantage, boon or bane effects of the resonance. To know that one, we need the concept of mechanical vibration, the elements of vibration, different types of damping, and these topics we will be discussed in the reverse order. Not from the top to bottom, we will discuss from bottom to top. Now, to be comfortable with this presentation, you are supposed to be aware about these particular topics. But even though you are not from mechanical or civil structure, civil background, we can manage it with the suitable examples. Now, let us start our presentation with a common example, that is a washing machine, because this will give you some idea about what is resonance and how the resonance is affecting our day-to-day life. Let us see this particular washing machine having two parts, the washing part and also the dryer part. Now, you might have observed some vibration when the dryer part you switch on. Then I think most of you have the experience and what type of vibration you observe in that case. It will be the signal in time domains that will be like this. And what you do, you are also familiar to vibration and you have solution to avoid it. What you will do? I know that people will take the clothes from the dryer and they will redistribute or uniformly place it in that drum. So what is actually doing that process? You are making the mass distributed. Mass you are distributing means you are distributing, you are changing, or you are making the system having a different moment of inertia, because the K value, radius of gyration is changing, correspondingly moment of inertia is changing, and in effect that will change the vibrating nature of the system. So simply I am giving an example that to reduce vibration in our day-to-day life, we do redistribution or change of the distribution of the mass. That is one way of eliminating or attenuating vibration in this drive. That is one type. And one more thing you can see in this enlarged part, that is a vibration isolator. If you want to isolate vibration from the surroundings, you can use these isolators. So these two, isolation or redistribution of mass, that is attenuating the vibration. Then another type of vibration you may be familiar in the same device, that is once you switch off the dryer, then the dryer speed will be reducing, and at a different interval there will be some jerk for the machine. What is the reason for that? We already solved the problem with redistributing the mass, and during the operation that jerk or the vibration was not there, but once you switch off, there is some jerk, and again it is smooth, then after some time it is again jerking. So that jerk we have to analyze in this particular background, that is resonance-free mechanical structure. So what you are actually doing, you are reducing the spindle speed of this particular device, and suppose it is coming from say 2880 and it is gradually coming to 0. So in that case, it is crossing certain natural frequency modes of this system. Once your operating frequency matches with the natural frequency, resonance happens. And there will be multiple modes, and you can see that whenever it crosses different modes, this type of jerks are observed. Now, the frequency domain representation of different harmonics are shown here. Now, here you can see that different peaks are there. Once you cross this peak, the resonance comes. Now, what I am suggesting that, what is the nature of the vibration you observed? Is it in the regular interval or not? One student told that if the harmonics are in the regular interval, but the jerks are not in the regular interval, what is the reason for that? Have you thought about that particular phenomena? Even the harmonics are uniformly, evenly distributed, the vibration you are seeing in different interval. The reason is very simple. Your spindle is not rotating in the same RPM. It is reducing from say 2880 to 0 in different speed, or it is uniformly decreasing. So the time taken from 2000 to 1500, 1500, that will be different from 1500 to 1000. That means the time taken to cross the uniform intervals of frequencies are different for the these rotating system. So since the system is rotating in reduced speed or gradually reducing speed, the time taken will be different. So that is a very interesting thing. Even though the harmonics are of equally distributed, evenly distributed, the time taken for the dryer to cross that harmonics are different because that dryer is rotating in reduced RPM as the time progresses. So what is the possibility to reduce resonance? So you may have some idea, because I am introducing this example to get a clear idea about what is resonance and how it can be eliminated. So you may have some idea how the resonance can be eliminated from the system. But one thing is, you can have you can avoid the coincidence of this operating frequency with the natural frequency of the system. Then the other thing is, I will introduce you one more situation related to this dryer. From 2880 to 0, once you switch off this dryer, this jerk is observed. Why that jerk is not observed once you switch on from 0 to 2880? What may be the reason for that? Any idea? Since it is a webinar, you cannot respond immediately, I know. But you think in that particular direction. If this phenomenon happens, that is from 2880 to 0, jerks are observed in different harmonics. But from 0 to 2880, that jerk is not observed while switching on the machine. The reason is very simple and it is very interesting, and it can be applied to avoid resonance. That is, the time taken to cross that resonance period is a matter of the response of the system. If you can easily or quickly cross that particular zone, the resonance impact will be less for the system, because as the time progresses and the coincidence, the match is there, the response will be more severe. So what are the things we came to conclude in this particular slide is, by redistributing the system, you can reduce vibration. By providing the isolators, you can reduce attenuate vibration. The other thing is resonance that happens in the harmonics, and it is the coincidence of the operating frequency and the natural frequency of the system. Different modes will be there, harmonics will be there. To avoid that one, we have to provide, either we have to avoid the coincidence, or we have to reduce the time of interaction between the harmonics and the operating frequency of the system. Now, resonance, what are the applications? Is it advantages or disadvantages for the day-to-day life? The bonon. Here, mechanical domain, we have different examples, that is musical instruments. If you take a guitar, you may have seen different types of strings. Actually, the different strings are providing different modes, because the thickness, the material, and the nature, the cross-sectional area, that will be different for different strings. That is one option to change the frequency. Then another thing is, you are changing the length between the supports by putting your finger at the different places. That means the distance between the supports are changing, so naturally the mode will also be changed. So in musical instruments, almost all type, we are using the phenomenon resonance. So we know that what type of resonance gives what type of the sound, and that mapping that gives the beautiful music from the instrument. This is something related to mechanical domain. We know that the wavelength, the frequency, everything is matter. In the case of earthquake, the wavelength may be meters. But if you take in this small the sound waves and all, it will be in nanometers, micrometer levels. So we have to be very careful about dealing this vibrating system, because many parameters are influencing the the performance. Now, if you move to that electrical domain, RLC circuit, where the resonance is also a factor to tune the radio. So the capacitive and inductive reactance, that is equal, and we are getting proper tuned system to accept the signal of a particular station. So RLC circuit, we are also using this resonance to tune the system to catch the corresponding frequency. Now, there is another interesting topic, static and dynamic comparison. Many of these structures we are constructing to withstand the static condition. Students from mechanical background might have studied design of machine elements, and they may be very clear about how to design different aspects according to the force acting on the system, the torque acting on the system, etc. And in the practical applications, they may be giving, say, 2 or 2.5 factor of safety to get the exact dimension for the construction. But in reality, it is operating in the dynamic condition. If it is operating in dynamic condition, what is dynamic condition? The force is fluctuating. Even though the magnitude of the force is much less than this maximum permissible limit, if it is operating at a particular frequency that is coinciding with the natural frequency of the system, is capable of producing disaster to the, or it may damage the structure. So it is not only matter the force that decides the stability of the system, the level at which the force is acting, the nature of the fluctuating effect that decides the stability of the structure. So we have to be very careful dealing with dynamic system. Static systems, it's okay, the maximal load what is acting that you can take and the factor of safety can be applied, that is sufficient. But once you move to the real world, where we are not able to define what type of the force is acting, in that case, we have to be very careful about the dynamic effect of the forces. Now, we discussed what are the different possibilities to avoid resonance. Then one thing I want to tell you that in many of these electronic equipments, in the manual it may be written that the operating frequency may be, say, less than 40K, 50K, like that. What that 40K, 50K means? The natural frequency maybe is that particular value, and you are safe to operate that particular machine below that particular natural frequency. For example, if the natural frequency of the device is, say, 40K, then the operator has the freedom to operate that machine up to 40K. But if that natural frequency is less than, is somewhere in 10K, then if you operate above 10K, there may be chance to coincide a natural frequency with the operating frequency. So one way to avoid resonance is make a very high natural frequency, so that during that operation it never matches with the natural frequency of the system. So that is one way, or that is the easiest way in of these equipments. Move to the highest, but many times it may not be possible. In that aspect, we are discussing this particular webinar, and I think you may have some idea about different types of vibration. I will just give you the basic concept. There are different types of vibration. One is called, say, this is free vibration. And in free vibration, simply see a mass is suspended on a spring, and the spring is connected to a reference plane. Once the mass is disturbed from this particular position, either to the bottom or to the top. For example, we are pulling it the downward position. What will happen? There will be stored energy in the spring. The spring will be under elongation and will try to pull the mass back to this equilibrium position. So assume that you are pushing to the top, there will be compressive force. At this particular point, the spring will try to push the mass to the downward direction. Suppose in this top point, you may be okay, I think it is visible. You may be releasing from here. The corresponding point is here, x0 at time 0. And once you release it, it comes to the equilibrium position, but it cannot stop it because of the inertia. It will move in the same direction for some more time. And once it reaches, that inertia force will be 0, and there will be spring force, and that will again bring it back. So that this movement from these two extremes that will happen in the normal case. But we know that during each movement, some energy is dissipated from the system. That dissipation of energy is called damping. So if there is damping in the system, what will happen? Once it moves from this top to bottom, some energy will be dissipated. That means this much of amplitude you cannot get in the other side. And correspondingly, as the time progresses, you can see that the amplitude will keep on reducing, and this type of vanishing or disappearing wave can be observed. Now, just see what is this particular wave. It contains two components. One component is the repetitive nature, sinusoidal signal. For example, say cos omega t plus sin omega t, whatever it is, that will be visible here. Now, in the case of undamped, if there is no energy dissipation from the system, this particular signal will be visible. But there is one more component that is dissipating the system, that is called the damping component. So this is superimposed with this particular repetitive nature that gives the domain this signal. So an underdamped system, you can see this type of reduced amplitude as the time progresses. This is your time domain signal. Now the time taken between two identical points, that is called time of oscillation. If it is damped oscillation, we mark it as TD, and the amplitudes x1, x2, x3. These things are very familiar to mechanical engineers in their dynamics or machinery subject. Now, this time domain signal is useful to calculate the damping ratio, logarithmic decrement, etc. that I will tell you. But that is the time domain. But once you convert this time domain to frequency domain using signal processing method, then you will get the natural frequency of the system. So simply convert a time domain signal into a frequency domain signal. The peaks will be there. That peaks are the representation of the natural frequency of the system once you do the free vibration. So how you do free vibration? Here mass is disturbed, or it is displaced from the equilibrium position, and that is released. But in the case of structures, we will simply hit with the impact hammer and will find out the type of response from the system. The basic equation is visible here. So we will move to the next part. What we do with the free vibration. This is something related to the mathematical analysis, but I will limit the presentation to this domain with this slide because mathematics is not suitable for all branches of engineering, or may not be comfortable for many people participating in this webinar. So if you take just x1 by x2, that will be the ratio of the successive amplitudes. Now, the T2, that is the time in the second cycle, that is the time for the first cycle plus time for one more cycle TD. So what is there on the right side? Right side, it is only e to the power of zeta omega n TD, because all other terms will cancel out. This e raised to negative zeta omega and T1 e raised to negative zeta omega and T1 in the denominator and numerator, that will be cancelled out. Now we are taking the natural logarithm. Once you take natural logarithm of this expression, only the power will be retained. So natural logarithm of x1 by x2, that is natural logarithm of the amplitudes of the successive oscillation, that is equal to zeta omega and TD. This particular term is called a logarithmic decrement. So logarithmic decrement, we got an expression. This is not a direct tool to measure the damping performance of a system. So we will move to the damping factor. And in damping factor, we will substitute proper values here. We will change TD by 2 pi divided by omega d, because omega d, that is 2 pi by TD, and omega n, we are substituting omega d, we are substituting in terms of omega n, and finally we will get an expression like this. And rearranging this particular equation, taking zeta into one side, we will get expression for damping ratio. So damping ratio, that is a clear measure of how much energy is dissipated from a system. Now, This is the case of a free vibration. Now let us go to a forced vibration. What is forced vibration? You are continuously applying force in a systematic way to the system. For example, if you take the test specimen, it is mounted, and once you apply the load here in the sinusoidal form, this is electrodynamic shaker. So shaker that provides force in the dynamic nature. So what will happen? It will be hitting this part in the regular interval, and there is a sensor, force sensor is placed in the top. That force sensor that will be capturing the force applied on the system, and this will be the pattern you will get in the time domain. But the response of the system that is obtained by providing or mounting an accelerometer in the top, and the accelerometer that will give the displacement or velocity, even acceleration of the system, and then that is provided in the next time domain. Observe these two. You can see that one part is starting from this extreme end. This is from the other end. That means there is phase difference. That means you may be pushing the system, by the time the system may be moving down. So this is very interesting phenomenon. The phase difference between the force signal, that is the excitation signal, and the response signal that gives the nature of the damping happens in that particular system. So if there is no damping, both will be in the same. So that means the phase value will be 0 if the phase difference will be 0 if there is no damping. Okay. And the natural frequency will also be same as the damping frequency. That is omega by omega n, that will be the same value. We know that damped frequency, if there is damping, what will happen? It will take time to move forward. Some resistance will be offered to the system, so that the time taken will be more to complete one oscillation. Correspondingly, the 2 pi by Td, omega d value will be that will be low. That means oscillations will be affected. The omega d and omega n, that will be different in the case of a damped vibratory system. So we discussed simply basic things, that is free vibration and forced vibration. And one more thing, you may not be familiar in the undergraduate program, that is called regenerative vibration. What is regenerative vibration? We are giving energy into the system. Once you apply force continuously to a system, this is the input part. And the system will be damping energy, or it will be dissipating energy, that is the other side. So what will normally happen? If both are equal, there will be no resonance, the amplitude will be uniform. But initially, the input energy will be much high than this damped energy. So what will happen to the system? That the energy will be accumulated and it will keep on increasing. And at one particular point, it may be matching. The reason I can tell you with the example of this limiting cycle. From here, the damped energy is getting increased. And at one particular level, it is coinciding with this input energy. So what I am telling that all dampers, we will discuss different types of dampers. All dampers perform high level when the velocity is more, displacement is more. When the amplitude is more, the damping will be more. So here you can see, as the amplitude progresses at one particular stage, you can see that almost all the input energy is dissipated, and further increase of this amplitude is not taking place. But whether your system is stable to go to this much of displacement, that is the challenge. Many of the structures cannot have that much of deflection, before that it may fail. So we have to think whether our structure can go up to this particular level or not. If it breaks in this much of this particular displacement, then our system is not stable. So we have to dissipate more energy so that the limiting cycle can be generated in this small region or close to the start, then it's okay. But if the time is more or the amplitude is high, then there is a chance of collapse. Okay, so that is one thing I want to tell you. That means the damping should be better, otherwise the amplitude will be more and the system may fail, damage will be there for the structure. Now, regenerative vibration. What is regenerative vibration? I want to tell you a simple example, that is a group of people are moving, a group of people are marching on a narrow path. Suppose one person is falling down. What will happen? Once a person is falling down, the next one who is coming back will be putting their legs on him, and finally some casualty may happen. So what is the basic reason for that casualty? Whether the fall of the person or the legs that is placed by those who are following him. The failure of the first part caused the failure of the second one, and that caused failure of the third instance, etc. That successive situations we have to be careful in the vibration analysis. That means the first failure caused the second failure, and that may be more severe, and that will cause more severe failure in the follow-up period. So here I am just comparing this particular situation with the machining process. Here there will be some undulations, and once the tool is just hitting, there will be undulation, and this undulation that will cause variations of the chip thickness once it moves one more time, so that it will be reflected in the remaining rotations. This is the case of a turning operation. This can also be visible in the case of a boring operation. The only thing is the tool is moving in the opposite side, from the center towards out. The turning it is from outside towards the center. Anyway, the failure of the first instance that caused failure in the remaining successive rotations or whatever it is. So this type of failures are called a regenerative failure. In vibration, it is called a regenerative vibration. Okay, now let us move to the next part, that is ground resonance. We may know that the helicopter, once it lands, there will be ground resonance. You may be familiar about this ground resonance examples that is available in many YouTubes. Here, the rotor is rotating, and once it lands, there will be a resonant frequency between the reflection from the ground side, this side, to the rotor part, so that the stability of the rotor is affected, and that will be fluctuating. And I think in the end of this presentation, we can see that video, because the change of this view that may be disturbed. So that here we can see that the rotor is rotating and it is landing. Some waves are getting reflected, and finally the failure happens to this aircraft. To avoid that one, what they are doing, that they are providing some dampers in the bottom. Once you look from the bottom side, you can see some dampers here, and also some dampers in this region, because it is allowing some fluctuation, so that instead of maintaining the consistent nature orientation, it is just changing it intentionally, so that the resonance is avoided. So the testing of this ground resonance in real situation, experimental part, that I will show you after this presentation. Now, what are the requirements you need if you want to really conduct experiment on vibration? First of all, I already told you that there should be an accelerometer to pick up the response that is mounted on this structure what we are analyzing, and the other end that will be connected to DAC system. So there should be some DAC to connect this particular signal processing unit. And if you want to conduct this type of free vibration experiment, you need an impact hammer, and there will be an electrodynamic shaker that will excite the system according to the nature of the frequency we are giving to it. It can be a sinusoidal or constant speed. It can be a sweeping signal. Suppose you don't know the natural frequency of a system, one simple experiment you can do with this electrodynamic shaker is just to sweep the frequency from 0 to say 1000. In between, it will show the resonance. That particular frequency is the natural frequency. So just sweeping that interval and the signal processing part, that is slightly complicated, but just I tell you the concept is so simple. Using this system, electrodynamic shaker, you can excite it at different frequencies, different modes. In the constant mode, you can constant frequency excitation is possible. You can have the sweep. Anything is possible with the proper signal generator. And the response you can capture using this accelerometer and can connect to this is NI9234. I think that can be connected to signal processor. So just you have a idea about what is this particular equipment used for. Now we have to move to the next slide where suppose a car is moving on a level road, even the road is so smooth, there will be some undulations. That undulations will be visible to the, that will be experienced to the passenger who is traveling in that one. Even though the shock absorber is there, there will be some effect of that road undulations on the comfort of the passenger. So we have to model it. Even though we are dealing something with the experimental part, we have to model before do the proper experiment. So I'll just invite your attention to the modeling of a vibratory system. And this is a simple example. A car is traveling on a road and undulations are reflected. And if you model, there will be three elements. One is the mass, the other one is the stiffness, and also the damping part. If you take a car, there will be the tire that is connecting, which will also act as a damper that reduces the undulations to the suspension or the chassis of the vehicle. Okay, now we'll see the three different parts of a vibratory body. One is the mass, and mass is connected to a spring, and once you move downward, it will oscillate, and in between there will be some energy dissipation that is called damping. So these are the three basic elements of a vibratory system. There will be stiffness, there will be damper, and there will be mass. Now, just to model a single degree of freedom system. Here, in the single degree of freedom system, what is basically a degree of freedom? You already know that the number of independent parameters to define the position of a particular body during oscillation is called degree of freedom. So the minimum degree of freedom is 1. So the position of the mass can be obtained simply by knowing the x of t value, the displacement that is sufficient to know the position of the mass. Here, the angle theta is sufficient to know the position of the bob in a simple pendulum. That means these two are the examples of a single degree of freedom system. Now, here, if you take this particular free body diagram, we are just taking this mass and draw the free body diagram. The spring is stretched as the mass is moving towards right. That means the spring will try to bring this mass back to this initial position because the spring is stretched, it is elongated. So there will be a force acting towards left, that is yes, your mass, the mass is visible, and the kx, that is the spring force that will be acting the body towards left. Then the body is moving towards right. So what is happening here? Mx double dot, that is the inertia force that is acting towards right. So these forces will be balanced to get the stability of the system, or we are not providing any other force to the system, means these two will be balanced. So mx double dot plus kx equal to 0, that is the basic governing equation in the absence of the what you call damping. So the solution of this differential equation, omega n equal to root of k divided by m, this value you can easily get by the solution of this differential equation. My objective is just to tell you what is the modeling of this one and how the natural frequency is obtained. Now, just to see this particular bridge, that is caused a casualty, Tacoma Bridge. Actually, the bridge was capable
No audio. Dear participants, due to some technical error, the host lost his connection. Please wait for a few minutes. He will be back. Sorry for the inconvenience. Hope you understand.
Okay, thank you, sir. സൈഡിൽ കയറിയിരിക്കട്ടെ.
Is it audible to you now? I think it is. I think it is audible. Extremely sorry for the interruption in between. Some technical failure happened. Please log in or please pin with the Biju CV Biju login ID because some technical issues are there. So I hope now you are comfortable. Dr. Biju CV, that login ID you can pin it. Okay. Now we were talking about the bridges that failed because of this resonance effect. And now we will just move to the next part, that is different types of dampers. Once the mass is moving through a fluid medium, there will be some resistive force that prevent the movement or that is affecting the movement of the body. So that principle is used in the case of a viscous damping system. And there will be hysteresis damping, that is also very popular, where you are loading and unloading the system so that two different paths are followed. The area between the paths, that is the energy distributed from the system. So these two are the different commonly used dampers, hysteresis damper and fluid damper, or it is also called viscous damper. Then the another part is the Coulomb's damper or the friction damper, in which the frictional force that prevents the movement that is utilized for the damping process. So here, three different dampers that is very popular in the academic textbooks are presented. In addition to these two, you can have another two more different dampers. I want to introduce two more different dampers. One is called particle impact damper, the other one is tuned mass damper. So what is particle impact damper? There is a derivative of a single mass damper. Actually, what you are doing is you are filling some particles inside a cavity, where that cavity is either mounted or a cavity is made inside a solid body which is vibrating. So there will be a primary structure in which either you can mount or you can make a cavity, and in the cavity you can fill the particles. And what will happen once the primary structure vibrates? Once the primary structure vibrates, the cavity also vibrates, and that will transfer energy from the boundary to the particle. And the particles will collide each other, and also it will collide with the surrounding boundary. So there will be momentum exchange between the surrounding boundary with the particle, and particle to particle also collision happens. So this collision, this inelastic collision, that is also a very nice method to dissipate energy from a vibratory system. So if you are very much interested in this particular area, it is a novel area, you can go through this particular textbook, that is particle damping technology, in which you will be able to know how much the energy can be damped and what are the parameters. So many parameters are affecting in this particular structure. For example, the size of the particle, the number of the particle, volume fraction, then the velocity with which it collides, the surface of the primary structure. Many parameters are influencing the energy dissipated from a damped energy dissipated from the primary structure. Then another one is tuned mass damper. What is tuned mass damper? In which a heavy mass that is allowed to oscillate. Now you can see a big building, a multi-stored building that is balanced. For example, in the case of earthquake and all, they are utilizing this heavy mass that is suspended from the top, so that there will be phase difference between the movement of this particular building and movement of the heavy mass. So this is another derivative that is called tuned mass damper. Not only for the big civil structures, it can be used for any vibratory system where this space is available. Now, we will move to the core area, the resonance, how the resonance can be eliminated. Here, two possibilities are there. Either you can play with the structural dynamics or you can play with these operating conditions. The easiest thing is, if you know the structural dynamics, ask the operator not to operate in that particular region where the natural frequency exists. That is the easiest method, because if the operator is well aware about the natural frequency, or if he can identify the resonance in the onset, he can move to different operating conditions. But there are certain conditions it may not be possible because the operator may not be there because the new generation systems are operated automatically. So operating conditions cannot be changed as and when we want. So in that case, we have to go back to the variation of these structural dynamics. What are the basic components? We have the mass, stiffness, and damping. And how you can change the parameters, either passive or active, semi-active. In passive, we are not giving any energy back to the system. The system itself is using the part of the energy to attenuate it. And active, we are providing energy from the outside. Now, attenuation or elimination of the resonance. So two aspects we are discussing. One is attenuation, where resonance already occurring and the effects we are reducing. The other part is elimination. Elimination means we are avoiding the possibility of the occurrence of resonance. So the first one, attenuation, is very common and it is practiced in more than 100 years, and different types of dampers have developed, from Lancaster damper to many new generation dampers. Attenuation is possible, but elimination is very interesting, and it is a novel design how to eliminate resonance using smart structures, because this possibility was not existing years back because this type of materials were not there. It was developed recently. So the research can be concentrated on this particular area, how to eliminate resonance. We already discussed something, mass distribution can be modified in the case of a rotating system. Stiffness, how we can change that, I am going to discuss now. And the dampers, we already told. And operating parameters, if there is an operator, in the onset of the resonance, we can change the operating parameters. Then another one is excitation time. As quickly as possible, run away from that mode or particular running, you will be safe from resonance. So many of the time these things may not be possible because you have to continue that particular natural frequency, that particular mode. There may not be any operator. So we have to find out a foolproof system which can operate continuously at any frequency without affecting the stability of the system. Now, these are the three different options. You have either you can control the mass, you can control the damper, you can control the stiffness. If something is vibrating, sometimes we may add some more mass to the system. So root K by mm is changed, you will get a different natural frequency. You can change the damper, you can modify the stiffness. But modification of stiffness is not so common in the literature. So I am inviting your attention to this area. And one more interesting thing, I want to show you the video. That part is how to maintain what you call the conservation of momentum. Once a person is rotating in a rotating chair, once the hands are stretched, the moment of inertia will be more, so that I omega value that will come to reduced value. So what I am telling you that if it is stretched, I value will be more, so the speed will be reduced. And once it is holding close to the chest, then I value, the moment of inertia will be low and the speed will be more. So even though speed of a particular position is low, once you close his hands, the speed you can see that it will be increasing without excitation, without any external support. So the redistribution of the mass is very, very interesting. If there is any vibratory system, if you can modify the position of the mass very quickly, then that is an option to modify or to attenuate these vibration or the resonance. Now, before that, I invite your attention the modeling of a 2 degree freedom system, where multiple degree of freedom system starts with the 2 degree of freedom system. So the easiest way is to analyze a 2 degree of freedom system, because this will give you an idea how a system or vibratory system is working. Here M1 and M2 are the two masses connected by 3 different springs, and it is displaced. And what will be the nature of the oscillation? I will tell you how M1 and M2 will move. What are the different frequencies? For that, we have to take the free body diagram of the first mass, and you have to make the corresponding equations. What we are doing is the spring K1 will be elongated, K2 will be either elongated or it will be compressed depending on X2 is greater or less than X1. If X2 is greater than X1, the spring K2 will be elongated, it will be under tensile force, and the mass M1 will be pulled towards right. But if X2 is less than X1, the spring K2 that will be compressed and there will be a pushing force towards left. So we are assuming that X2 is greater than X1 and we are making the first equation, M1 X1 double dot, that equation. It's very familiar equation in vibration. Now the second part, we are taking the free body diagram of the mass 2, where again three forces are acting. One is the spring force K3, then K2, then inertia force M2 X2 double dot. Now again modifying or rearranging the equation, we will get the corresponding governing equation. Now how we convert this particular equation, linear equations, into matrix form? That is very basic example, because M1 is related with X1 double dot, M2 is related with X2 double dot. There is no other cross relationship. There is no M1 X2 double dot. So the matrix you can easily form M1 0 0 M2. Here X1 double dot, X2 double dot. So the conversion of a linear equation to a matrix form, because we are using computers for the analysis. So in that case, we need to transform everything into matrix form. So this is the mass matrix, and this part is the acceleration part. And here the corresponding coefficients of X1, X2, you can take it. So that 1 part will be multiplied with 1 here, then it will be multiplied here, K1 plus K2 X1, then correspondingly K1 plus K2 X2 minus K2 X2. That whatever the equation you have here, that can be reproduced with this matrix. Simple part. Now, for the simplicity, because of the shortage of the time and all, I am reducing the variables K1, K2, K3 into a common variable K, and X1 that is equal to X1 sin omega t, X2 sin omega t. Then the expression can be reduced to this form. And I am not going to this detailed mathematical part. You will get the natural frequency omega 1 equal to root k by m, and second part omega 2. Second natural frequency, second mode, that is equal to root 3k divided by m. So what is the relationship between first and second frequencies? It's a multiple of root 3 times of the first two. So there will be one frequency where the value magnitude is root k by m. The second mode, that is root 3k divided by m. So we know how fast the system will oscillate, because the time frequency is known, means you can calculate the time. What is the cycle time for completion of one oscillation? That is available from this omega 1 and omega 2. But that is not sufficient in which direction it moves, because it has the freedom to move in that particular linear direction any of the ways, either towards right or towards left. So in that case, I am going to that analysis where the amplitude ratios are taken, x1, x2. Once you substitute the value of root k by m in this equation, you will get x1 by x2, here also x1 by x2. What is the meaning of x1 by x2 equal to 1? Either both will have the same values, or for this particular example, I can say that x1 equal to 1, x2 equal to 1. The equation is simply x1 by x2 equal to 1. So I am interpreting it as x1 equal to 1 and x2 equal to 1. What is the meaning in this particular scenario? One will move some distance towards right, that is say 1 unit. So M2 that will also move towards right the same unit. So M1 and M2 will move towards right in the same phase, same magnitude. That is the first move. Are you able to visualize it? M1 and M2 may be connected as a rigid bar here, will be moving together towards right, and after that it is coming back. How you can interpret it is coming back, because x1 can be -1, x2 can also be a -1 value. Then there also x1 by x2 value will be 1. So M1 and M2 can either move towards right in the same magnitude, or it can move towards left in the same magnitude. Anyway, there will be no phase difference, and the direction will also be the same. The separation will also be the same, or you can simply say that the spring K2 is acting as a rigid rod that avoids the relative displacement between M1 and M2. What about the second mode? Second mode is root of 3k divided by m, and x2 x1 by x2 value, that is -1. Sorry, okay, it is -1. That means x1 you can take as 1, then x2 value is -1, or vice versa. X1 is 1, x2 is -1. That means mass 1, that is moving towards right 1 unit, by the time mass m2, that is moving towards left same unit 1. That is m1 and m2 are approaching each other. How much m1 is moving towards center? M2 is also moving the same unit towards the center. If M2 is moving away from the equilibrium position towards left, M2 is also moving towards. That means it's a very interesting movement. The x1 is 1, x2 is -1, or vice versa. The ratio is -1. That means the phase is almost opposite in nature. So this should be there in your mind once you develop a resonance-free structure, because you should know how the vibration happens, what are the movements to the system. So this part is just a modeling of a simplest multi-degree freedom system. Now I'm just going to smart materials that is used in this particular development. We have the sensors, actuators, and controlling unit, and all the three together that forms the smart structure. So we should have some mechanism to sense, and there should be some mechanism to control and apply that one through the actuator. The sensing elements can be temperature, pressure, whatever it is. So this is the general topic, nothing exactly focused on this vibration area. Now, what are the smart materials? Here, piezoelectric materials, we know once you apply the force, the system produces some current voltage, and the reverse also happening to the system. And rheological materials are mainly two. One is electrorheological, the other one is magnetorheological material. Here you can see the magnetorheological material where the carbonium ion particle that is suspended in oil medium, that will be randomly floating in the medium. Once you apply the magnetic field, it will be aligned and it will act as a chain. So no fluid across the chain can move from one side to the other. So such a strong barrier is constructed, and this is the basic working principle of magnetorheological fluid. Instead of magnetic field, you can apply electric field, then electrorheological fluid will also behave in the same manner. So I am concentrating this particular material and its characteristic for the resonance-free structure. And shape memory alloys that are also there. So we will be just closing this particular slide, that is different smart materials are there. It is your choice to find out what type of materials can be used for the construction. Because the construction, the principle will be the common, the mechanism will be common, and depending on the availability of the material, depending upon the modeling easiness, you can also have the choice of the material. So I am going with the magnetorheological fluid. Now, this is another simple schematic diagram. You can see that this is a MR fluid that is floating, and no magnetic field is applied to the system. And, the structure inside there is another cantilever. So if you consider this outer portion is fixed, that you will be acting as a primary cantilever. And inside the primary cantilever, I am putting one more cantilever, one inverted cantilever here. So cantilever inside a cantilever, that is the design of this particular element. And what you can see that once I apply the magnetic field north and south, the particles are aligned, and the thick region, it will be almost a semi-solid level that will prevent the deflection of this inner bar, and that behavior is used to attenuate resonance. So this is a very typical design. There is a hollow portion in which MR fluid is filled, and also coaxially one more bar is placed. Then once you apply, in the absence of the field, it is free to oscillate, the resistance will be less, the damping will be less. But once you actuate the system or magnetic field is applied, then it will be a semi-solid region, and it will offer resistance to the oscillation. Now let us see this particular characteristic curve of this magnetorheological fluid, that is lots make you can make a product, and you can see that as the magnetic field increases, the yield strength also, yield stress also increases, and around 35 kilopascal it is saturated. Beyond that, whatever the magnetic field you are applying, there is not much use. So you have to limit it. The operating region is around 300, 350 kiloamps per meter. So what is happening here that you are applying magnetic field and you are achieving yield stress to the maximum, so that further movement is restricted. Now let us come to this particular diagram. This is the core part I want to share you. If you are really interested, you can work on this particular design. Here we have a fixed element, and this fixed element is basically a cantilever. So compared to A, B will be deflecting more if you apply a dynamic force here. This is the dynamic force, fluctuating force. Once you apply the dynamic force here, what will happen that this cantilever will oscillate in this particular direction. Now, definitely A will be almost zero, it is the fixed end. B will be much higher because it's the free end. We know the deflection Q by Pi, that will be the value of this oscillation you will get, the deflections you will get, the frequency you will get. Then correspondingly what we will do, we are connecting another bar close to B so that B and C will be almost of the same deflection. Then C and D, that is another cantilever, a cantilever inside a cantilever. So what will happen to D? D will also oscillate in this region. Now, if there is any fluid in this region, that will be squeezed out to the sides once it is moving up. Once it comes down, the fluid in this region, that will be squeezed on the side, to its sides. So if the fluid is in low viscous nature, in the absence of the magnetic field, this resistance will be much less. And once you apply north and south, what will happen? We can see that in the presence of this magnetic field, this region will be totally solid level. That means resistance offered by CD will be on CD, that will be much high. Correspondingly, the deflection at the C and B, that will be limited. That means same load if you apply here, the deflection will be less. What it indicates, the stiffness will be improved. Higher stiffness, that will increase the natural frequency of the system root K by M. It's a very typical design. You should be very careful about applying the magnetic field, and region there should be sufficient space to move the inner part. Otherwise, it will be hitting these sides. You may get negative results and all. But this particular design is capable of producing tunable natural frequency to a structure, and I can show you the exact values. If you load the FRR, frequency response function, from 288 it comes to 294. You may have some doubt that this is a very minimum change. 288, 294, very minimum difference you are getting by applying this. This is only a representative demonstration. If you apply higher magnetic field, this is only 3.5 amps current is applied to some toroidal magnetic core. So if you use electromagnetic material having high magnetic intensity, you can get more shift. That means from 288 you are getting 294, and moreover you are getting some additional peaks also, 39 like that. That means different frequencies you can generate. You can tune your frequencies, and you can have different stiffness. How you calculate the stiffness means you have the frequency response function. From there you can split this amplitude part into real and imaginary, and the imaginary part will have a negative amplitude here, and applying that amplitude in this particular equation, you will get this value of K, that is the stiffness, and you can apply the corresponding equation to get the frequency. So either you can get the frequency directly from FRF, this experimental part, or you can calculate and find it out. So what I am going to share you that if you provide an element like this in your structure, and if the excitation frequency you don't know, if you are able to sense that variation, you can make a corresponding shift of the natural frequency of the system so that the coincidence can be avoided. So that is the basic beauty or the intelligent nature of this particular component. So how you make a system resonance free? Either you don't operate the system be above the natural frequency. For example, the set condition is 75K or 45K, don't operate beyond that value, then you are safe. The other possibility is avoid the coinciding time or minimize the interaction time, then also you can reduce resonance. These are the two possibilities. Without much expense, you can do it. But if you are brilliant, if you want to take some challenge, then you can go for tuned mass or tuned frequency structures, where you are giving the freedom to the operator. You operate at any frequency. The system is stable because we are not depending what the operator is doing. We are depending the inherent property of the structure and also the tunable mechanism incorporated to it. So no need to put all the elements with this type of resonance-free mechanism. In a structure, there will be n number of elements, and you have to find out which element that provides the maximum contribution to the performance or the frequency. You know that in a chain having a number of elements, the weakest element that decides the strength of the chain. The same manner, in a structure, you may have a number of elements, and whichever the element that have critical role, you can find it and provide this type of mechanism. What I am suggesting is no need to limit your design to this particular level. You can go to any level where you can change the stiffness, the system natural frequency can be defined. This part I already told you. And what is the summary? And because of the shortage of time, I'm not going to the next level. That will be continued in the next part of the webinar. We will continue the modeling of this type of systems. And today we discussed basically the concept of the mechanical vibration, then the elements of the vibratory system, different types of then types of damping, what is resonance, then modeling of multi-degree of freedom system, introduction of smart materials, different types of materials, then in which the subcategory is MR fluid, and how MR fluid can be used for tuning the frequency of a mechanical system. And what is the take home of this particular webinar is, you can design a resonance-free mechanical structure, but the procedure is slightly complicated. You have to analyze the system properly, you have to do the modeling, and you have to characterize the elements that is attached to it. For example, if you are using MR fluid, you have to do proper characterization, you have to develop the critical element, and by sufficient number of experimental trials and modeling analysis, definitely you will have a resonance-free structure. Thank you for the presentation. I hope you may have some, I think you may have some doubt regarding how to proceed further, and some clarifications regarding this presentation. I hope the coordinator can analyze the chat box, and if any doubts are there, we can discuss here itself. And please convey your comments, clarifications through the chat box.
If anyone have any questions, please unmute your mic and ask questions directly to Biju sir.
Either you can ask the questions now itself, or you can send the queries to the mail. We can respond within one or 2 days time. Anyway, I hope some people are motivated to do something related to vibration. I hope that is the success of this particular webinar. I told you that some videos you can see. So this is the Okay, one second. Already told you that the ground resonance is a big issue, where the failure, the collapse of the helicopter can happen, where the and the ground that decides the stability. So once you look through this video, I think it is visible from the beginning. Okay. Now you can see that the stability is totally lost and it is completely broken. And you can see the analysis, some experimental setup is there where fear of ground resonance is studied. The same structure that was safe in the beginning, gradually the amplitude gets increased, and at one particular stage, it is totally collapsed. So this is one video, and one more part. The bridge I told you, that is Tacoma Bridge, the bridge that was capable of the bridge that is capable of withstanding 120 is visible to you. Okay, the bridge that was capable to withstand 120 km/h wind speed, but that failed 65 km/h. The thing is, it is not the maximum permissible limit, whether it may be force or wind speed, whatever it is, that is not deciding the stability. In the dynamic structures, whether it is crossing the resonance or different modes, harmonics, that decides the stability. So here you can see that after the opening 7 years, it performed very well, and the total collapse you can see in the end of this video. So, any queries? Hello, I think it is audible to you. Actually, vibration isolation means you are making it separate from the surrounding structure, so that the transmission that is limiting. So our objective is, hello, yeah, is it audible? Okay. So what I'm suggesting that there are so many methods to avoid or to reduce attenuating vibration, but if you concentrate to avoid resonance, that will be much better than attenuating the resonance, because if there is no resonance, the need of damping or the need of attenuation of the vibration not so attractive, not needed. That will not be so required to this situation. So the objective is to make this resonance free nature. So I think there will be some doubts in your mind as the time progresses. You may be something not is there. So anyway, I'll take this opportunity to thank all the participants from different places, spend your time, valuable time on this area. And on behalf of Jyoti Engineering College, Mechanical Engineering Department, and SAE, I would like to thank you, and also the coordinators, and Sakriya and Sukesh P, who did a lot of work right from the beginning to this moment. And I hope they will support you for clarifying your queries through mails. Thank you. Hope we can discuss. Thank you once again.
Thank you, Bijay sir, for this application-oriented webinar which enlightened our knowledge in the field of vibration. Thank you all for actively participating in the webinar conducted by Jyoti Engineering College, Mechanical Department of Jyoti Engineering College in association with SI Collegiate Club. I also thank our management, principal, and our HOD Biju sir for their support to conduct this webinar. Feedback link will be shared through your registered mail on the next day. Once again, I thank everyone. Thank you all.